Is the presentation visible?
Yes, it is.
Okay. Thank you. So, as I had mentioned in the last yesterday, we are now going to discuss a technique, a set of formulations to statically analyze the program code to find opportunities for global optimization. We have seen how to represent the code in terms of the control flow graph and how to represent basic blocks in terms of directed acyclic graph and its modification in terms of the value numbering scheme, so that using those we can do a number of local optimizations like constant propagation, constant folding, and local common sub-expression elimination. But what we need to do is a large number of global optimizations which is impacted across the basic blocks on the control flow graph. Now, naturally, if it goes across the control flow graph, across the basic blocks in the control flow graph, then we need to take care of how does the impact of data definitions and data use work with the control flow on the program. Naturally, the control flow cannot be completely decided statically because it depends on the data. And depending on the data, certain parts in the program may or may not be taken. So data flow analysis is always an estimate-based method, that it tries to estimate certain data flow quantities based on a conservative approach. That is, we try to estimate different data flow quantities in a way so that for all possible inputs, at least that much of flow is guaranteed to happen. So let's see how to get around with this. Here we will try to understand the data flow analysis, and we'll see that there are two basic approaches of doing data flow, which is either forward or backward. That is, I can traverse the program from beginning to end or from end to beginning, that kind of. And there are confluences which are inclusive or exclusive. We will define what confluence is. And with that, we will illustrate the data flow solutions for a number of common and very useful problems like reaching definition, available expressions, live variable analysis, which will not only be useful in optimization, but it will also be useful in terms of register allocation and assignment, definition use chain, copy propagation, etc. So that's what we are going to do. This is the outline which you can see on the left in every slide. Okay. Now, first we formally define an execution path. We all understand what a path in a program means, but to formally state that, we will say an execution path from a point P1 to a point Pn is a sequence of points P1, P2, Pn, where Pi is a point immediately preceding a statement. I have a statement, so immediately preceding that, I kind of conceptualize a point Pi, and Pi plus 1, the next point, is the point immediately following the same statement. Or this is what will happen inside a basic block. Otherwise, Pi could be the end of some basic block and Pi plus 1 is the beginning of the successor block. Naturally, in general, there would be infinite number of paths to the program, and because there could be loops, flow back, and as such, there is no bound on the length of the path. So the program analysis summarize all possible program states. All possible program states means that whatever state the program could take based on all different possible inputs that the program can take, which is obviously infinite. So the program analysis, the static analysis, will summarize all possible program states that can occur at a point in the program, but it will have to do that with a finite set of facts, because you cannot analyze a finite set of facts. So it is clear that no analysis will be necessarily a perfect representation of the state, because we are trying to estimate the quantities which have infinite possibilities using only finite set of facts. So we will have conservative estimates for the same. Now, just to illustrate the formal definition of the path, here is the program that you have seen before. We are using that same example, and these are the P0, P1, P2. You can see that before every statement, we have marked the points here. There's a typo. I'll just ignore it here. There's a typo. So a path could be P0 to P1 to P2. Up to this point, it is fall through. So P0, P1, P2. Then I have a condition. So it can either be true, in which case it goes to 106, which is P6, or it could be false when it goes to P3. So it goes to P3. Then we have go to 124. 124 is here on the rightmost column, and it is P24. So this ends here. Or a path could be P0, P1, P2. Then it could go to P6, P7, P8, P9, P10, and you have a condition check, which might take you to 120, which is P20. You can see here, P20, P20, P21, P22, P23, and it brings you back to 104, which is P4. Then you have P5, after which it takes you to 102, which is P2. Right? So it could continue to go like this, and potentially you can have paths going through this which are potentially infinite. A similar example through the control flow graph view, you can trace here and see different example paths. Now, the main purpose of data flow analysis are two. One is it helps in program debugging also. So it can, this data flow analysis results may help to get different debugging information. For example, we often get in the debugger that a variable may not be defined when it is being used. So we can even statically get an estimate for this by doing a reaching definition analysis. That is, we see, given a definition, what are the points in the program where that definition can reach. If there is a point in the program where a variable is being used, and there is a potential that from the beginning of the program up to that use of the variable, there exists a path where it may not have been defined, then we can say that it is potentially uninitialized. Right? So this kind of program debugging can be possible. Information can be generated even statically from the data flow analysis at the compile time itself. And certainly the other reason, which we have already mentioned, is optimizing the programs, like constant folding, complete propagation, common sub-expression elimination, and so on and so forth. I'm sorry. Now, let us try to understand the data flow analysis schema. So a data flow value, whatever I define to be the data flow problem, a data flow value for a program at a point represents an abstraction of the set of all possible program states that can be observed at this point. This set of all possible program states must be noted. That is, it must hold for all possible inputs that it can have. So this set of all possible data flow values is called the domain for the application that we are considering right now. For example, if we are considering a reaching definition problem, the domain of data flow values is a set of all subsets of definitions in the program. It is reaching definition. So which definition reached to a particular point? So there will be several definitions. And if I take the whole set of definitions and form the power set on that, set of all subsets of the definition, then those are the potential domain values at a particular point for the data flow on reaching definitions. Now, in order to do this, we start by defining two sets for any specific problem. One we call the inset, other we call the outset. The names are self-explanatory. So if S is a statement, then inset in S is the data flow values that exist before the statement, the point right before the statement. And out S is the set of values that exist at the point right after that statement. So for every statement, I can get in S and out S. I want to make an estimate for the in S and out S. And the data flow problem is to find the solution to a set of constraints that would exist on in S and out S. And I want to do that for all statements S that goes first for every block and then for the entire program. So I first computing this within a block maybe is easier, more straightforward, because you do not have to consider the control. But once we have done that, then we use some more constraints to apply it on the entire program. Now, extending this notion of in S and out S for every statement, we define in B and out B for a block. So clearly, if S primed, a statement S prime follows S in a block B, then we will have in S primed is equal to out S, because there is fall through. So whatever comes out of a statement certainly is what goes in necessarily in the next statement. So this is what will happen in the fall through within B. Now, over the control flow graph, when we cross a block boundary, basic block boundary, so let's say in B is in S0 and out B would be out Sn, where S0 is the first statement of the block and Sn is the last statement of the block. So look over the block, it is the first, whatever comes into the first statement, we say is what is coming into the block. And whatever goes out of the last statement is what goes out of that block. So in B and out B are data flow values right before and right after the block B. So Extending this notion, we can say that while within the block, we can compute in S and out S across the blocks, we can across the program at the block level, we can compute the in B and out B. And estimating these quantities is the basic task of the data flow problem. So data flow technique is more like a schema. It's more like a formulation. And in this, there are two kinds of constraints that happen. One set of constraints are based on the semantics of the statements. There are statements of varied kinds. There is assignment, there is copy, there is conditional statement, unconditional go-tos, and so on. So every statement has a different semantics, and those will work as constraints on the particular data flow problem that we are trying to focus on. So these are typically called transfer functions because they transform every statement, semantically will transform the data flow quantity in the way the statement works. The second kind of constraints are based on the flow of control because within the basic block we have fall through, but across basic block we have conditional and unconditional jumps, and those will be the constraints which tell us how to estimate the data flow quantity. Now, a data flow schema overall will comprise the following 5 entities. The first is a control flow graph, which is obvious, the basic blocks and the overall control flow graph. The second is, what is our direction of data flow? Are we doing it forward or we are doing it backward? Third is the data flow values that we are trying to estimate. Fourth is the confluence operator. What is confluence? Confluence is when we go for the control flow graph, then certainly at the basic block boundary, we'll have either branch out or margin of controls. So those are the confluence points. Like the name comes from like the confluence of rivers as would happen. So it is a confluence of control flow, and we will have different confluence operator, typically union or intersection, to deal with the flow issues based on the particular problem. And finally, we'll have transfer function of each block. We have transfer function of each statement, and taken together, the entire transfer function of each block, which will transform the in set onto the out set, will be considered. So these are any data flow problem, any schema for the data flow problem we need to define. We'll have to define these 5 quantities. Just to remind, we will always compute safe estimates of data flow values. That is, a decision or estimate will always have to be conservative. That is, if we apply it on any program state, which is potentially infinite, or if we use that to make a change in the program, then it will never lead to a change in the computation that the program does. Right? So it has to always preserve the program logic. And mind you, this applies over infinite program states. So this assumption of conservative estimate is very, very important. Right? One second. Now, the safe values may be either subsets or supersets of actual values, which is based on the particular data flow problem we are solving. So to introduce the whole paradigm, let us take the example of reaching definitions problem. So we define a few notions. We say we kill a definition of a variable A if between 2 points along the path there is an assignment. Because I have one definition, let's say I have defined the variable, and then the control flows, and I have another definition of the variable. Now, naturally, when I have the second definition, the earlier definition no more holds. So we say that that definition is killed. So a definition D reaches a point if there is a path from the point immediately following D to P, such that D is not killed along that path. So then we will say that it has reached. If it is killed along the path, it does not reach. For example, there could be unambiguous and ambiguous definitions of variables, like A assigned B plus C is an unambiguous definition of it, because it will always change A. Whereas if I have star P assigned D, then this is an ambiguous definition of A, because P may point to A or it may point to variables other than A as well. Right? So if it points to some other variable, then naturally it does not kill the above definition of A. Okay. So this is the basic notion that we want to solve. And here you will easily understand that being safe, being conservative, is to compute the superset of definitions. That is, it harms less if I estimate that a definition reaches a point where it actually does not. But if I miss out a definition reaching a point, then I will have dire consequences based on the actions that I take on that observation. For example, this can very easily happen. For example, if you look into this small code here, if A is equal to B, I define A to be 2. Else, I again check A is equal to B and I assign A as 4. Now, this definition, A assigned 4, as you can see, will never be reached in a real control flow. Because if A is equal to B, then it will assign A to 2. Else, if it is not equal to B, then obviously it will not satisfy the check of A equal to B again. So whether or not A is equal to B or A is not equal to B, A assigned 4 will never actually be reached by the control flow. But in our estimation, we will not take care of this fact, because we really are not doing a simulated computation. We are just doing a static analysis, and we will not be able to infer that A is assigned to 4 will never be reached by the control flow. Right? So we will estimate that to be a definition which can be reached and which can reach someone. Okay. So what are some of the possible applications of reaching definition? One that we will see subsequently, it can be used in building the use definition chain. That is, if definitions reach a point, then every statement that it reaches, I can see what are the variables that are used in that statement. That is what is occurring on the right hand side. And based on that, I can say that this definition is used in this statement. And that will have a lot of advantages to go with. Then I can have constant propagation. For example, if I have a definition of a D where variable V is assigned C, which is a constant. Now, if all definitions that reach the point N where V is used has this definition, D, that is the only definition that reaches this point N, then I can conclude with my conservative estimate, which is a superset, that V is always going to be a constant C and propagate this C onto V. Okay. Now, mind you here, it is very important to note that we are doing superset of conservative estimates. So it is not possible that a definition might reach N, which we are missing out. So it will be safe to replace V by C if this is the only definition that reaches N. Then we can obviously detect uninitialized variables. If we have a use where no definition of that variable reach, then we have an uninitialized variable being used. We can do loop invariant code motion. What does that mean? Suppose, consider this loop and consider the statement N where X is assigned A plus B. Now, there will be definitions of A and definitions of B that reach this point. Now, if I find that all definitions of A and of B that reach the point N happen to be outside the loop, if they're outside the loop, all of them, then it is safe to move this particular statement outside the loop. Okay. If there is any definition within the loop which reaches N, then we cannot do it. But if all definitions that reach N, all definitions of A and all definitions of B that reach N are outside the loop, I can take this statement and put it outside the loop, which says that since all definitions are outside the loop, within the loop, this is an invariant. That is, it does not matter as many times as I compute A plus B, I will get necessarily the same value. So it does not vary as the loop iterates. So it's a loop invariant, and I can take it out of the loop and thereby optimize, because if the loop runs 10,000 times, I will have 10,000 times doing the addition of A with B and assignment to X, which can be avoided by only one computation outside the loop before entering the loop. Right? So these are the kind of with reaching definition, these are the kind of optimizations and analysis, further analysis that you can do. Now, let us look at the actual formulation. So, remember, we are doing reaching definitions. So, we need to do an estimate, which is a superset. Right? First, let us look at, first let us define these two terms, Gen B and Kill B. So let me go to the next slide, define these terms, and then we'll come back to this formulation. So Gen B is a set of all definitions that are generated in B. That's a basic semantic meaning. So what are these? Which is a set of all definitions inside B that are visible immediately after the block downwards exposed. Which means that if I go through the block from top to bottom, and then at the end of the block, these are the definitions which will be visible. So if a variable has two or more definitions in a basic block, then only the last definition will be downward exposed, because certainly the other definitions will get killed mutually as the control will progress. All others are not visible outside the block. So only the last one will be visible, and that is what will make to the Gen B. So Gen B is, as I said, is a set of definitions that are visible outside the block B immediately after the block. So it is again that superset I mentioned, that if I have set of all definitions, then Gen B is a subset of that, which comprise the set of all definitions inside B that are visible immediately after the block. Kill B is a union of definition in all basic blocks of the flow graph that are killed by an individual statement. Right? So kill B is again an estimate, a conservative estimate. So if I have a variable x being defined as in DI in a basic block, then this definition DI kills all definitions of the variable x in the program except DI, all of them. So mind you, the killing definition is in the basic block, but the kill definitions could be anywhere. So because I do not know what the control flow is, so I'm just making a conservative estimate that this definition that I have in the basic block, the definition DI that I have in the basic block B, can potentially reach any definition in the program and kill it. Right? So I consider all of them killed. Okay, so these are the two sets. So based on these sets, I I provide the basic transformation constraint. I said there are two kinds of constraints. One is flow and another is transformation. So this is the transfer function constraint, out B. What will come out of B with all this? One is the definitions that have been generated. Remember, multiple definitions, if they're there of the same variable, only the last one will survive in Gen B. So all that it comes out, all that is generated, union those definitions that have come into the block and have not been killed. Some definitions that may have come into the block have been killed, so they will be taken out. Others which came into the block and maybe they have been used in the block or may not have been used in the block, doesn't matter. They came into the block and they were not killed. So in B, difference kill B. Union, Gen B, whatever definitions have got. So this is the transfer function. This is a transformation that the basic block is providing to the entire reaching definition flow. The first one is a flow constraint, which says that what happens at the control at the flow control points. So it is very clearly that if P is a predecessor of P, that is the control comes from P into P directly. If P is a predecessor of P, then whatever I have at the output of P, whatever definitions I have at the out P, will be a part of in P. And mind you, multiple blocks may be predecessor of a specific block when this is a merge point. So all of their out sets will be taken union of into the in set of this particular block. So this is the flow control constraints, and the other is the transfer function constraint, which simultaneously give us a set of two equations where there are two unknowns, in B and out B. Only problem here is that these are set quantities, so these will have to have a set value. Gen B and kill B will be computed from the basic block through the linear fall-through analysis. Now, for doing this, now naturally set equations cannot be directly solved by algebraic techniques. So what we will do an iterative solution. That is, we will start with an estimate, compute in B and out B for all the blocks, and then again use them to compute the next iterate value of these variables and keep on doing that till we reach a fixed point, and till we reach a point where the in B and out B of none of the blocks change. Right? So we can see that this is a forward DFA problem because we are using predecessor. So the control is coming from the previous block to the next block. So it is going forward. So since we are using predecessor here, this is a forward DFA problem. Or in other words, you can also say that out B is expressed in terms of in B. So this is a forward problem. And the confluence operator we were talking about here in the flow, how are we combining the quantities is by union. Right? So the direction of flow, mind you, does not imply traversing the basic block in a particular order. And the final result actually does not depend on the traversal of the basic blocks either. Now the question is, since we are saying that we will do an iterative solution, so the iteration has to start with some initial values to be able to, otherwise if everything is unknown, then where do we start? So we say that in B is a null set, is an empty set for all B, all basic blocks. That is our initialization. Why do we take it as null set? We take it as null set because reaching definition, the safety or the conservativeness of the reaching definition is doing a superset. So we would like to start with the minimum possible value and grow it. Because if we had started with any other value, then there is a possibility that we are including something which will finally not be included in the result. So we start with the least possible value that any in B can have, which is empty. Right? So this is the formulation. Please remember this formulation. These are the definitions we had. So just to give you a little bit of practice on the gen and kill set. So this is a basic block B, which has 4 definitions. And there are 6 other definitions in other basic blocks. This is, the left side in other blocks, this white box is not necessarily one single block. These are 6 definitions which could be in one block, they could be in 2 blocks, they could be in 6 different blocks. Right? So what is my domain? My domain is the set of all definitions, D1 to D10. There are 10 definitions in the program. Right? Now, what is the gen set? The definitions that have been done and have not been killed within the basic block. So A is defined here, B is defined here, C is defined here, and A is redefined here. So which clearly says that D4 within the block itself, the D4 kills D1 because this definition D1 will not be visible downward. So we have only 3 definitions that are generated. That is D2, D3, and D4. So that is my gen. What is my kill B? Kill B is any definition that I have in some block somewhere will get killed by a definition. So D1 is a definition of A, so it will kill all definitions of A. So it will kill D4 here, and it will kill D9. Right? So D1 will kill D4 and D9. D2 is B, defining B, so it will kill D5, the definition outside the basic block. D3 is C, and C is not defined anywhere, so it does not kill anybody. Oh, it does. I'm sorry. I'm very sorry. D3 kills D10. C was defined here. So D3 kills D10. So D10 is in the kill set. And D4 again kills D1 and D9. D1 and D9. Right? So in this basic block, these are the 5 definitions which are killed. And these are the 3 definitions which are generated. Right? So this is my basic starting point of doing the computation with every basic block. Compute the gen and kill set, which can be easily done. Now for the confluence, let's consider that I have a basic block B4, where the flow is coming in from B1, B2, and B3. So naturally, each one of them will have an outset, out B1, out B2, out B3. So in B4 will be the union of out B1, out B2, and out B3. That is what the first equation says. In B4 is out B1, union out B2, union out B3. Now, in terms of the transformation, if in B4, let's say is PQ and Z, definitions PQ, Z, and I'm sorry, if gen B4 is AB and kill B4 is Z, okay, then what will be out B4? It will be gen B4 AB union in B4 minus kill B4. So PQ Z difference Z, which is PQ. So I'll have AB PQ. Okay. So that is how the outset will get defined, will get computed for the particular block. So this is I hope you understand the data flow equations for reaching definitions now. So let us quickly take a look at an example. So this is a small program. It does not do anything meaningful. It's just for the purpose of illustration. So as I'm starting, I'm in pass 1, the beginning, starting. Naturally, all insets initially are set to null. So in B1 is null, in B2 is null, in B3 is null, in B4 is null. There are 4 examples. And I compute gen and kill set for everyone. So gen set here is quite obviously D1, D2, D3. Kill set will be any definition of I, J, or A. So D4, D5, D6, D7. D4, D5, D6, D7. Okay. So if I have that, then what will be my outset? Gen union in minus kill. Now, obviously, here in the first iteration, since in is a null set, indifference kill will always be a null set. So outset will be same as the gen set. I mean that in this pass, this will always happen because inset for every basic block is a null. So I have outset, which is same as the gen. At B2, the gen set is D4, D5, and the kill set is any definition of I or J, which is D1, D2, D7. D1, D2, D7. Outset is same as the gen set, D4, D5. In B3, gen set is D6. Kill set is any other definition of A, which is D3. So outset is also D6. In B4, the gen set is D7. So the kill set will be any definition of I, which is D4 and D1. D1, D4. And outset is D7. So after pass 1, we will have these other quantities, and then we will have to apply the flow confluence to get the new estimates for the insets and again the new estimates for the outset. So I go to the next slide. which is the first block computation for pass 2. So this is pass 2. Dot 1 means I'm doing it for the basic block 1. So here, naturally, in black is what I had, and in red is what I'm computing now. So here, the flow comes from entry. So at the beginning, obviously, there is no definition. So inset continues to be null, and therefore no change in the outset. Let's go to 2.2. I'm doing it for the second. So here, this is what I had. Now, gen and kill sets obviously does not need recomputation because they're based on the block. So they don't change on the passes. So only the in and out sets will henceforth change. So what is the inset? The inset is the union of the predecessors of B2. What are the predecessors of B2? Predecessors of B2 are B1, and because of this loop back, it is B4. So B1 had an outset D1, D2, D3, and B2 had an outset which is D7. This is from pass 1. So I'll take a union of these two, and it becomes D1, D2, D3, D7. This is my inset. So what will now be my outset? Gen union. So D4, D5 goes in. Then inset minus kill set. So from the inset, I'll strike out all those that are in the kill set. So D1 is gone, D2 is gone, D7 is gone. Only D3 remains. So outset now becomes D3, D4, D5. You can see D3 has got added to this outset. Okay. Let's do it for block 3. Now in block 3, so these two have, block 1 and block 2 have got computed already. In block 3, this is in black is what he had. And now what is his inset? Its inset is whatever was the out of is the out of B2, which is D3, D4, D5. D3, D4, D5. And so the outset of B3 will be gen D6 and in minus kill. So D3 goes, you just remain with D4, D5. D4, D5. So you have D4, D5, D6. So D4 and D5 have got added in this pass. Finally, I will go for B4, which had outset, which was D7. Now, in the inset, I get the flow from B3 as well as from B2. So out of B3 and out of B2 will be considered together. So I have D3, D4, D5, D4, D5, D6. So I have D3, D4, D5, D6. This is my new inset now. So my outset will be gen D7, and then I strike out whatever is there in the kill set, that is D4. So I'm left with D3, D5, D6. D3, D5, D6, D7. Right? So this is my, so I've completed pass 2, and this is my, these are my new estimates and in and outsets. Then I go through it again. And I can see that this will not change. Here, since I have D3, D4, D5, and this has got D6, D7 also added because of this backward loop. So D6 eventually gets added to B2, the out of B2. Similarly, B3 was earlier D4, D5, D6, but that does not change here, neither does B4. Okay. So I come to a point which is the fixed point in terms of this computation, and I have found the reaching definitions, and you can, since it's a simple flow graph, you can easily reason about them also. For example, if you see here, what is downward exposed is D2, D3, D4. What is downward exposed here is naturally D4, D5 will be there. And you also have D3, the definition of A can flow through this. So you have D3. And you have D6, the other definition of A, which comes from B3 onto B4 back in here and go through this. So these are, but no other definition like this definition of I cannot flow through here because it's got given. Similarly, if you consider this block, then you will see that these definitions of I and J, which are outward looking, for D4, D5 will be here, and you have generated D6. Right? So this is where we have actually finally computed the reaching definitions, estimates of the reaching definition. In this case, I think it happens to be also an exact quantity, but in general, it would be just an estimate. That is a superset. And we know which at every entry and exit of the basic block, what are the definitions that have reached. So this is the process that we have talked of, is written in the form of an algorithm. So for initialization, in B is set to null and out B is set to gen B. We have already reasoned that in the first pass, in B being null, naturally out B will be just the gen B. And then we use a flag to see if there is a change that has happened by remembering the earlier out B and computing the new out B. So we keep on doing the computation based on these equations and checking if out B has changed. If it is changed for any block whatsoever, then I put the change to true and continue to do the next pass. If it has not changed for any of the block, then I'm done. I've been able to find all the basic, all the gen kill in out sets for the basic blocks, primarily the in and out sets of reaching definitions for the basic block. The data structure that can be used is, this could be a bit array. So the indexes of the array are different definitions, and the entries are 1 or 0 if it is included or not included. So basic, the set representation data structure is what is commonly used, the bit vector, which has a very compact representation. So we can use long bit vectors for doing this computation. So let me stop here and see if there are questions. Is there any question on this? On the overall data flow formulation and for the, particularly for the reaching definitions? No questions? Surprising. Okay, good. So let us have a break for 5 minutes, and then we will continue with the next problem in the data. Okay, let us continue. So we have gone through the first problem in data flow analysis, that of reaching definitions. Now we'll take a look at a different problem of available expressions, which will be useful in terms of common sub-expression elimination. So naturally, the domain in this is a set of all expressions in the program. That is all different right-hand sides that you have. It is a forward flow problem, and the confluence operator will be intersection. Why is it intersection? Because it harms less if an expression is actually available at a point and I do not estimate it. But if it is the other way, that an expression may not be available, but I put it in the estimate, then based on that, when I do common sub-expression elimination, I will certainly have wrong computation in the program. Right? So it is, you can see that the estimate here is of the other kind. It's not a superset, rather a subset. So formally, we define that an expression x plus y, that is just representative, is available at a point P if every path, not necessarily cycle free, can go through cycles as many times as it desires to. If every path from the initial node of the program to P will necessarily evaluate x plus y, and after the last such evaluation, prior to reaching P, there is no change, no further definition of x or of y. It's intuitively very clear. This is just formally saying that x plus y is available at a point P if on every path from the beginning to P, x plus y will be evaluated. And after the last such evaluation of x plus y, before reaching P, there is no change in x or in y. Naturally, kill is quite obvious. A block will kill x plus y if it assigns or may potentially assign to x or to y and does not subsequently recompute x plus y. And quite naturally, the moment you assign something to x or to y, it will kill x plus y. But it is also possible that the block might recompute x plus y again. If it does not do that, then it kills x plus y. And a block generates x plus y if it definitely necessarily evaluates x plus y, and does not subsequently redefine x or y. Quite, these are quite obvious intuitive things, but being formally defined for that word. So this is useful for global common sub-expression. So it's V1 is computing, just in a small example, V1 is computing 4 star I in T1. And B3 also has 4 star I. And these are the paths. One is directly here. So if it follows this path, naturally 4 star I is available. What are the other possibilities? One is it goes through a path where there is no assignment to I. That path could be of any length, going through loops and so on. But if on that path there is no assignment to I, then again I do not need to recompute 4 star I. I can assume that it is available. Or it goes through a path where I is assigned, but 4 star I is again computed. Then also 4 star I is available. But mind you, here, in terms of actual elimination problem, we will have to be careful because here the 4 star I is available in T1, whereas in this path, 4 star I is available in T0. But in any case, 4 star I would be available in B3. But if it goes to some path where I is assigned and 4 star I is not recomputed, then it will not be available in B3, even though there is a direct path from B1 to B3 which makes 4 star I available. Right? It has to be available on all paths. Right? So this is how we will compute the gen and kill sets within a basic block. So let's say I have a statement x assigned to y plus z, and q is a point before that, p is a point right after that. And at q, let's say the gen set so far computed is a set A. So as I cross this statement, I will add y plus z to this set A, because this is getting generated. And x has been assigned. So from A, after adding this, from A, I will remove all expressions in the program that involve x, because those are actually getting killed by this. So A minus all expressions that involve x. And the resultant set A is my gen set at P. And I keep on doing this along the straight line flow of the block to get the entire gen set. The kill set is similar. At Q, let's say it is A. As it crosses this, naturally, y plus z has been generated. Surely, right? So it is no more killed. So if it were there in A, I take it out. So A minus the set containing y plus z. Then I add to A all expressions that involve x, because those are getting killed. So I added them to the kill set, and that is my kill set at the point P. And I keep on doing this as I go from the beginning to the end of the basic. Again, example of these sets. These are the same 10 definitions we had used earlier. Now we will be looking at the expressions only. So I have f plus 1, a plus 7, b plus d, d plus c, a plus 4, and so on. So I have 10 expressions. Do I have 10 expressions? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 expressions, right? Because b plus d is there twice. Right? So I have 9 expressions here. That is my domain. The gen set here is f plus 1. A plus 7 is not in the gen set because after that A has been changed. So it has been removed from the gen set, b plus d, d plus c. Kill set is anything involving A, B, C will get killed. So A plus 4, A plus B, E plus A, C plus F, A plus 7, all of those which involve this will get killed by this. Okay. Now the data flow equations. We'll say that out B is same because we are doing a forward problem. Right? So the out B is same. That is gen union in minus kill. That will be the property of the forward. The confluence is now intersection, because I have to take the list estimate, that is what is available on all paths. In reaching definition, it was what was coming in from any path. Now it is all paths. So I have to take intersection of the outset of the predecessors to get the inset of the basic curve. Now, this will be done if B is not an initial curve, right? Because otherwise it does not have anything to proceed. And obviously, no matter what the program is, in B1, where B1 is the initial or empty block, it will always be null. So no expression has been computed till that time. So it will always be null. For the rest, now note it here, the initialization is with the set of all expressions, universal set. Why is it so? Because you remember in the reaching definitions, we have started with a null set and then started growing from the null set to the bigger sets. Here, we start with the biggest possible set and we'll keep on shrinking to the possible set, because here our underestimate is a subset. So we start with U, which is a set of all available, all expressions in the program. A similar example, so three controls coming in. Quite obviously, this is the intersection. This is a small hypothetical example. In B is A plus B, P plus Q. Gen is X plus Y, and kill is A plus B. So X plus Y will come from gen. From in B, A plus B is killed, removed. So it becomes X plus Y, P plus Q. Now, this is just to, here I have not shown in terms of every possible point sets, but I just show the possible available expressions. For example, here I have, I think this is bubble sort, code of bubble sort. I minus 1 is available here. I minus 1 that goes like this. And that is the only possible way to get into here. So you can get I minus 1 at this point, I can see. Then 4 star J goes to 4 star J here. So I've used the same colors to just illustrate. So different available expressions are shown by this analysis. And obviously, once we have that, we can eliminate them. This process we have seen earlier by the defining variables of the available expressions and do the common sub-expression elimination. And this is again the algorithm written in the formal way. So initially for B not equal to B1, I have out B is U minus the kill set, because universal set is already there in the in B. That is how we have initialized. Since universal set is already there, it does not matter what is there in the gen set initially. Because if something is there in the kill, then that will not certainly be in the gen. So the remaining are already included. So it is U minus kill. And then you go through this iteration exactly in the same way. So in this way, we can compute the available expressions in the program by doing the data flow analysis. Let me stop once to see if there is any question. Any questions, friends? Okay. So let us take the next problem, which is the live variable analysis. Now, I did talk briefly about the liveness of variables earlier. So here we are formally defining it. A variable x is live at a point P if the value of x at P could be used along some path in the flow graph starting at P. Otherwise, x is dead. This EM is a type. So if the variable x is live at P, it will be considered live if, as I go forward from P, then there is some point where x is being used. Then x is live, otherwise x is dead. You can see the difference with the available expressions, where the availability of an expression is based on the history, on the past, whether it has been computed earlier and it is available at this point. Whereas liveness analysis is based on future. I have a variable having a valid value. Will it be computed in future? So I'm going from this point onwards till the end of the program. Naturally, the set of variables constitute the domain of data flow values. Now, how do I talk about future? So what I do is, now I do a backward flow analysis. That is, I start from the end of the program and come backwards to see a variable that is used when in the past it was last defined. Right? So by making it, because certainly the computation in future is not possible. So I transform this problem as a computation in past by analyzing the flow graph in the backward manner. In B again is a set of variables that are live at the beginning of a block. Out B is a set of variables that are live just after the basic block. Now we give different names than gen and kill. We say gen is use and kill is def. That is, use is a set of variables whose values may be used in B prior to the definition of the variable. Because that means if a variable may be used in a basic block before being defined in that basic block, that means it must have been live. It has to be live on entry to the basic block. Right? So those are the variables generated as potential for live variables. Whereas def B, which represents the kill, is a set of variables which are definitely assigned values in B prior to any use of that variable. If it is used, then it is in the use. It needs to be live. But if it is defined before any use of that variable, then obviously any other use of the variable in the basic block will be this new definition. So if it is definitely assigned a value before any use of that variable, then it is in the defined set, def set, which is necessary in a kill. Now, you can see this is a backward flow problem. So now I will define in B in terms of out, because I'm going backwards. Okay? So it's a reverse flow problem. So in B is in the same way, use B, that is whatever has been used prior to definition, union out B minus def B. That is whatever is live at the end. From that, you take out the variables that have been defined in the block. So other variables must be live at the entry to the block. And for conference, since you're coming backwards, so your outset will be computed in terms of the inset. So out B is as union of the insets of the successors. So whatever has to go into the successors, that decides what has to come out from a basic block as live. So union of all of that will be the outset of the block B. So this is, once you have the definition and understand the way you will go in this, it becomes very easy to formulate this set of equations, data flow equations. Now, what will be the initialization? Naturally, now, since you are coming backwards, outsets will have to be initialized, and naturally, we will initialize them with null, because if we have to start and keep growing, then the outsets initial is all set to null. So an example here. So let us look at, first of all, outset is null everywhere. So if the outset is null, that necessarily means what is the inset is use union out minus def. If the outset is null, that certainly means that the second term is always null. So the inset is same as the use set. Now let us see what are the use sets. In B1, we are using M, N, and U1. M, N, and U1. None of them have been defined before being used. So that three of them together forms the use set. I, J, and A have been defined. So they are in the def set. Def set is. And after definition, they have not been redefined. So they have not been used either. So the def set is IJA. What happens with B2? It is using I before being defined. It is using J before being defined. So IJ will go in the use set. Okay? And it has no def set naturally. So the def set is now. In V3, the use is U2 and the def is A. In B4, use is AJ and def is I. And in is always same as the use set. This is my pass 1 on the code. Now in pass 2, what do I get? I have this. So in pass 2, in B1, I will have the outset as union of insets. Okay. Now it has only one successor. So since it has only one successor, the outset will be the inset of that successor, which is IJ. So the outset becomes IJ. Now what is my inset? Is from the outset, I'll have to take out def. So I take out def. So both I and J are removed. So out minus def becomes null set, and my inset remains same as the inset. So this is on B1. Now One point you have to remember, and that creates confusion at times, that you might tend to think that since we are solving a backward problem, we must start from the last block. No, it does not matter in which order you compute the quantities in the block. It may matter in terms of number of iterations you may need, but the final result will always be the same. Whether the problem is forward or backward is in terms of whether you are computing out in terms of in, which is forward, or you are computing in terms of out, which is backward. So even though we are solving a backward problem, we are computing from B1, B2 like that. Now, this is what you have in B2. So what is the outset? B2 has two successors, B3 and B4. So the inset is U2, inset is AJ. So the outset of B2 is the union of these two, in B3 and in B4, which makes it AJ U2. Take out the def from that, which is null. So it is use union this. So you have Aij, U2, all four included in the inset. So B1 and B2 are done. Then it is B3. B3 has only one successor, which is B4, whose inset is AJ. So outset here becomes AJ. So the inset is outset minus def. So A is removed, J remains. So with U2, I have J. So this is my inset here. In B4, B4 has two successors, the exit and B2. Naturally, exit does not have anything, so it is B2. So I have to check what is the inset of B2. So I get Aij U2. That is the inset of B2. Now, from this, I will take out def, which is I. So I goes Aj U2 and union Aj. So it is Aj U2. That is the inset. And with this final pass, this is my final result. So you can see that I mean, we can just again logically trace this program and see how things are. For example, here in the inset, the MNU1 has to be there. Why it has U2? Because you can go from this path, and this path, and you have U2 here being used. Right? On this path, it has not been defined. Actually, it has never been defined, so it has to be live here. So you can easily see that when you come to this block, the inset needs all these to be live, and if it is actually the beginning of the program, then you can easily say that these are the variables which have been, again in a different way, have been used without being defined. But in general, we are just taking a code segment, so the entry actually means that before that things have happened, and these variables have to be live at this point. Let us look at here. I, J, U2, and A. Ij will have to be live, otherwise you cannot compute them. U2, because you can go from here to B3, so U2 needs to be live. You can go from here to B4, so A needs to be live. So these are the quantities which clearly you can see is to be live. Here, U2 has to be live, what is obvious, but J also has to be live because you can go from here to here. On this path, it does not require, but on this path, it does require. And finally, here, as you can see, A and J have to be live. They are being used here. But I can go back from this point, go through B2, and come to B3. Right? So this is the backward trace I can do. So I will need U2 here. So U2 will always also have to be live at the beginning of V4. So that clearly, I mean, shows that it is. These are all intuitive observations, but we have this structured way of finding out a complete chart of what are the variables that are live at any point of time. You remember I mentioned while talking about the analysis for register allocation and assignment that we need to understand the live variables, because those cannot be, the values of those cannot be destroyed. So that analysis will come from this kind of a DFA. Then there are more like definition use chain. I think I'll skip that for you to study, where it basically is a which definition is used where. That is the problem that you are trying to solve. So it is a pair. The values are a pair, which is the variable that is being defined, and S is a statement that uses this variable. So in B is a set of such pairs. Statement S use variable X, and the value of X at in B has not been modified along the path from in B to S. So it's similar to live variable analysis, but here you are precisely finding out not only thus the liveness, but you are precisely finding out which definition has actually is being used. I mean, where exactly the value is being used. Similarly, outset is a set of statements that use variable X, and the value of X at out B has not been modified. I can insert an outset. So what is the gen? The use is a set of pairs such that S is a statement in this basic block that uses variable X. But naturally, if S uses variable X, then that is something which has been added from this block. And what is skill? That S is a statement which uses X, and S is not in B, and B contains a definition of X. So S is a statement that is using X. That is the basic definition of this pair. But that S is not in B. And you are defining X. So naturally, if you are defining X, then you are killing that. So it is this pair will not actually come to the def use chain. It's again a backward flow problem, because you are trying to look at the use which is in future, and so therefore this is the equation, what is obvious. The confluence is again on successor, and the confluence is union. So now I mean, once you get to the basic sense of the DFA, you will get this very easy. And initially it will have to be all null. So that is another problem. We will conclude with this problem, which is copy propagation. The copy propagation, because in the particularly in the automatically generated code, you must have observed by now that there are a lot of unnecessary copies are created, and those need to be removed. So what we want to do is eliminate copy statements of this form by substituting Y for X in all use of X reached by this call. So when can I do this? In two things. One is I'm copying Y to X. Right. So wherever this definition can reach, I will have to replace X by Y. Only then I can say that this copy statement is not required anymore. So that is the basic propagation. So we have to check for the use definition chain. Use U of X must consist of S only. That is where I'm trying to do the substitution. If there are multiple definitions of X that reach that point, then obviously I cannot do this replacement, because from a different definition, X will have a different value. So, but if S is the only definition that reaches this point, then at that point, I can replace the use of X by Y. And from every path, from the definition, from the copy S to U, the use, including that might go through U several times, but does not go through S for a second time, because then it becomes a new definition. There must not be any assignment to Y. Because after the copy, if Y has changed, then again, I cannot. So two things which are quite obvious. One obviously is that where I'm replacing, this must be the only definition, so that I can say that X is indeed replaceable by Y. And second is coming from this copy to the place where it is used and to be replaced. On that path, Y cannot be redefined. So there must not be any assignment to Y. Only then the copy is valid. So these are the conditions to check. Now, the first one we have seen how to do it. For the second one, that Y is not assigned, we formulate another data flow problem. So we say that the gen set is a set of all copy statements of the form X assigned Y in B, such that there is no subsequent assignment to either X or Y within B after S. Only then you can say that this copy is valid, that is X and Y necessarily always will have the same value. Then we say that this copy statement has been generated by the basic block. What is kill? Is a set of all copy statements which are not in this basic block, such that either X or Y has been assigned a value. So I have some copy statement in some other block. But in B, I have defined X again, or defined Y again, any one of them, or maybe both of them. Then obviously this copy is no more valid. This X assigned Y copy is no more valid. It's not valid to assume that X and Y would necessarily have the same value. Right? So that is killed. And certainly the universal set is a set of all copy statements in the program. That is the domain. The inset is a set of all copy statements reaching the beginning of B along every path, such that there is no assignment to Y or to X following the last occurrence of the copy on that path. Quite easy. And out is a set of all copy statements reaching the end of the block along every path, such that there is no assignment. That's in and outer. So this is again a forward flow problem, because we are defining copies and then checking out how they reach out subsequently. Yeah. So out is, as you can see, in will certainly be based on the predecessors, and our conservativeness in the estimate will say that if a copy actually is available and I don't find it, it's okay. But if I make an overestimation that a copy may not be available on a certain path and I estimate that, that will be a serious error. So it has to be the intersection of the outsets of the predecessors. So what is the inset of B1? Inset of B1 is obviously null, and the outset can be initialized too, because there is nothing initially generated. So outset can be initialized to U minus the kill set for every block. So this is finally the algorithm for copy propagation. For every copy statement, use the definition use chain to determine the uses of X that are reached by S. We have already seen that. For each use U of X, as we have found, we have to check U consists of S only. That is the first condition I talked about. And it must be the unique definition, which is copy that is reaching there. And if S is in inset, where B is the basic block to which U belongs, we have to ensure that S is the only definition that reaches this block, and no definition of X or Y appear on this path from S2. And no definition of X and Y occur within B prior to U in quantum, which is obvious. If S meets these conditions, then we can remove S and replace all users of X by. It's a simple algorithm, but it's a very, very powerful one in terms of getting to globally optimize the copies. So here there's a workout for this. You can go through that workout steps and see that. For this is from the book, and I have also marked out this in terms of the bubble sort example as well. So you can go through them and see how the global common sub-expression can be eliminated, and then the copies can be propagated along with that, so that I can actually optimize by removing those copies altogether. So the steps I've just shown. So let me stop here. This brings us to the end of this module. So let me see if there's any question. Any questions on the data flow analysis? So we have shown a very powerful, and these 5 problems are not the only problems to be solved by data flow. You can form your own problem and the formulation. But the key things to remember is how you define the inset, outset, generate set, and kidding set, and deciding on whether it's a forward flow problem or a backward flow problem. That is, whether you are computing based on past or you are computing based on future, and to decide on the nature of confluence, and then rest of it will follow from the basic algorithm for solving it is the same. And then you can combine this, like we showed in the copy propagation, that you can combine the solutions of multiple problems to solve any problem that you want to, that is statically analyzable, so to say. So this is, and so therefore it leads to the global solution of 3 key potential optimizations, that is constant propagation, constant folding, and global common sub-expression elimination. On the way, it also paves way for checking for uninitialized variable, loop in certain way, loop invariant code motion, and so on. So let me stop here. Prola, is there anything to tell them?